Okay, I believe that, yeah, we are now live. So, yeah, hello everyone, and welcome to today's LiveWork, where today we're going to be doing the final exam tree, no, sorry, exam tree of 3.091. But before we get started, we have we have some mistakes, which is like this guy here. This guy here is ALCL4. It can't receive It can't receive an electron because of reasons. Oh wait, no, sorry. Can't receive an H plus. I don't know why, but yeah, it can't receive an H plus somehow. But then, I believe the rest is correct. Oh wait, no, never mind. ASH3 actually accepts, which 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 makes this a base. And so of with the rest of this one here, this guy here, the answer is actually because yeah, this guy here is actually 8.49 times 10 to the power of negative 4 times 10 to the power of negative 4. What we can do is that, yeah, we can actually just ignore that. It we can just ignore that and then just put in 0.03 into the mix. And so when you just actually put it in, you can just write this as 0.03. And then we can just actually ignore this because this would be very small. The result would be that x would equal to, according to my calculations, it is 2.72 times 10 to the power of negative 8, no, negative 6 molars. So yeah, that's just basically the answer that I'm just going to be fixing. But yes, we are now going to be doing the exam tree of MITOCW. So yeah, let's just first save this guy first, and let's just create a new template. Let's see here. Yep, I am already live, which is pretty good, just in case that I'm not actually live. So yeah, I just made the new one here. Let's just remove that. Let's see. Yep, there we go. Oh yeah. Okay. So so I am gonna be putting in the first problem in, which is about 1 page long. So yeah. Um. Let me just put that in. There we go. And then just place it. There it is. That's the screenshot that I need. Boom. Okay. So let me just enlarge this a bit more. There we go. So, okay. Here we go. In the crystalline solids, no, sorry. In the two crystalline solids shown below, there are circled six different point defects total. Label each defect with its name. Okay. And yes, by the way, this thing is allowed by using your cheat sheet or whatever. But yes, you yeah, it is not really required because yeah, you can just memorize this a bit. This guy here It is it is an element which shouldn't be there, but it is the same atom as the rest of them. That is called self interstitial. Stitial. There we go. And then for this one here, we got we got a random element put inside into this lattice out of place. That would mean that it is a interstitial impurity. So we can just write that down. Stitial impurity. This guy here, this guy here, this one right over here. It is an atom, but it is placed within the lattice, which means that it replaced something. So that means that this guy here is a substitutional impurity. And then for this one here, if it is a blank, we call it a vacancy. See, simple. But then we have the ions. And yes, for the ions, no, sorry, for the ionic solids, there are two types. The first one is the Frankel. The other one is the let's see, what's the name? Hume rotary. No, wrong one. I don't think I write it. Oh, there it is. Frankel and Frankel and and Schottky defects. So yeah, Schottky Schottky is removing, but moving is called a Frankel defect. There we go. So that means that this one here is the Schottky defect. There we go. See, simple. Because like, yeah, this guy actually just removes the anion and the cation, just to make sure that the ionic solid is still balanced. So yeah, that's for problem 1A. That's pretty quick. So let me just go ahead and just add the new artboard. There we go. Part. This is still number 1, but yeah. We can just do this one. Let me just share this up. Place it there. So yeah. So we can later just discuss a little bit about it. Oh, wait, okay. That's not the new artboard. Yep, there we go. So here we go. You decide to buy a ring from a jewelry store down on Mass Ave. Draw on your deep knowledge of material science from 3.091. You decide that that a platinum ring is definitely the way to go. Unfortunately, the jeweler graduated from that school down the street. You are upset by their claim that the ring is defect-free crystalline platinum. Let's prove them wrong. Okay, first, you weigh the ring. It's exactly 2 grams. How many platinum atoms are in the ring? Okay, so how do you actually solve this? First thing that I see is that you want to actually to convert from the mass into numbers of atoms. To do that, you need to find out what's the MR of the sorry DMR of platinum, which is something that I don't memorize, but yeah, you can just look it up on your periodic table. Platinum, there we go. It has an MR of 195.084. Let me let me just zoom in. Oh, nope, command plus. There we go. So, okay. So this would mean that this guy should have how many platinums at how many platinum atoms are in the ring. That means that it's 2 grams divided by this MR, which means that you need to pull out your calculator and just plug in the numbers. So 2 divided by 195.084, what you get is that you have 0.01 molars. No, yeah, molars. No, moles. Because like, yeah, molars is something else. So yeah, 0.01 mole. But then it is asked how many platinum atoms? The atoms. So basically, all you need to do is to just to multiply the answer by the Avogadro's number, which is 6.02 times 10 to the power of 23, which means that it has 6.171 172 times 10 to the power of 21 atoms. And yes, I'm so sorry about the formatting, but yeah, let me just do something here. Can I just make this guy? Yep, I can make it a superscript. There we go. That is read much more better. So, okay, and so now see how many atomic sites are in the ring. Atomic sites. Well, basically, technically, according to my knowledge, the NPT. Wait, no, sorry, the atomic site. It should be the same as the number of atoms. That is that is from my theory, because like yeah the atomic sites is something that you can actually just plug in and out. So yeah. For me that it would be 6.172 times 10 to the power 21 sites. And yeah, by the way, I am not gonna check this for you guys. So you need to check it by yourself. Because I also don't have the solutions. But I will later just check it by myself. Okay, so D. It's a little chilly in the shop. 11 degrees Celsius. Assuming the ring is in thermal equilibrium, calculate the total number of vacancies and V that you would expect at the current temperature. The constant A has the value of 1.11. Assume the vacancy formation energy for platinum is 0.96 electron volts. Okay. So first thing that I see is that it has activation energy. That means that it has something like NV over N, which is basically the number of vacancies divide it is basically the fraction of vacancy would equal to A. Multiply that by E to the power let me just go and just give in the superscript in, just to make this a bit much more tidy. It would be EA divided by KBT. because we are dealing with atoms, not moles. So yeah, we use KB. And so with this, we need to do one of the crazy things, which is we need to first convert the yeah, we need to actually just to convert almost all the things. So yeah, it's 1.6022 times 10 to the power of 19. No, no. One actual volt is yeah, 10 to the power of negative 19. So yeah, 1.602. Yeah. Okay. So the let me just no, you know what? Let me just actually just put this guy back in. So that guy there, NV over N, which in this case we know what the N is, which is that the A here we know it's 1.11, and then for the EA we will just convert that first. It's that multiplied that by 1.602 times 10 to the power of negative 19. That would be 1.53792. No, you know what? 1.54 times 10 to the power of negative 19. Okay, so yeah, that's okay. So that's another superscript of the superscript. Can I actually make this into a nope? Nope, I can't. So yeah, we are just stuck with that. Divided by the KB. The KB, it is R over NA. R over NA. And then the temperature in Kelvin, which is 284 kelvins. And then we just need to plug in the numbers in. So let's just count the power. So its answer, divide the thing by R, which is 8.314, divided by the NA, which is 6.02. Wait, no, it's 6.02 times 10 to the power, yeah, 6.02 times 10 to the power 23. And then after that, that is the KB. And then we multiply that by the Kelvin, which is 284. So what we get is so what we get here is this entire thing here. Enter. There we go. That to the power of 39.2. So yeah, it is still a number, but yeah, we just need to figure out the rest of the thing. So we need to find out what the NV is. So NV, copy that, enter, paste. NV here would equal to 6.172 times 10 to the power 21. Oh wait, so yeah, 6.172 times 10 to the power of 21 multiplied by 1.11, multiply that by E. Oh wait, no, wait, it is a negative number. Why? Because it's the rule. So yeah, basically the power is a negative. So yeah, it's minus EA. So yeah, just making sure, just in case anybody got that wrong. There we go. So that would be E to the power of the answer. E to the power of answer. That doesn't make sense because because I forgot to put in the negative. And so what you get there is 64. Oh wait, no, assuming that. Calculate the total number, so yeah. It's 64,101. Or basically 6.4. Times 10 to the power of 4. And yes, that is the number of vacancies. So yeah, that is the answer for B until D. Let's hope that that's correct, because because I am not gonna check the real answers. So let's just add in the new artboard. Okay, there we go. Launcher 4. Screenshot that. Place that. Oh, let me just do that. There we go. Place. Boom. There we go. Extend this a little bit more. There we go. And so yeah, here we go. Let's go and do for E. Here we go. The jeweler is stressed out by your frantic calculations and eager to prove they are not cheating you. They hastily point out that the atoms that you came from those vacancies are probably sitting in interstitial sites in the lattice. You quickly pull up a paper that has measured interstitial concentrations in platinum. Okay. Note the units of interstitial defects concentrations are big M. Okay. Um Part 1. Estimate the formation energy in joules of an interstitial defect from the plot. How does this compare to the vacancy formation in PT, which was given above as 0.96 electron volts? Hint: assume that the interstitial defect concentration follows an Arrhenius relationship. That means that we need to use Arrhenius to solve this. And what is Arrhenius, you might ask? Arrhenius is the one that we just used, which is this one here. So yeah, let me just copy and paste that. But yeah, you might be thinking, wait, how do you actually solve this? Because like, yeah, we don't have any of those formation, any of those information, because yeah, what we got was a graph. The simplest way for me to actually to see this is, okay, we can, okay, so yeah, like yeah, one of them is the Lun. So we can actually just look at that. Probably we can just check that first. That would be a normal size there. So yeah, the ln of this guy, copy that, paste that, must equal to the ln of A. Subtract the thing by EA over KBT. Is that correct? I think so. It's the ln. So yeah, you're just taking the ln. So yeah. Okay. So with this, we can just actually rearrange this, just to see that actually this guy actually follows pretty much the same thing as the graph. So yeah, we can just go ahead and just put that in, and then minus EA. What's that? We can say that that is the slope. We can. And then we can just write in 1 over KBT. There we go. Add the thing by the natural log of A. And so, um, estimate the formation energy in joules. Okay. So we are trying to find the formation energy. So, so, so from what we know is that the formation energy is the slope, which we should, know. Watch, we know what's the slope here. Look at this. Um, let me just actually just reduce the size. Oh no. So yeah. Uh, so yeah, from this guy, um, I'm I'm just gonna change the color. There you go. No, Command Shift Z. There we go. So this guy here, from here, and then down to the bottom. And so what's the slope? It is always y over x. So the y here is actually just minus 20. And then the x would be 10. So the slope here, the m here that we have here, would be negative 20 divided by 10. That would be negative 2. But then we know what is negative 2. That is the slope here. That means we know what's the activation energy. And so we don't need to care about the we don't care about L and A. We don't care about the rest. All we need to care about is the slope, which is negative 2. And so we found out what the EA is. EA is 2 joules. Why is it at joules? The answer is I also don't know why. But yeah, we can say that it's at joules because the KB that we use. Yeah. We can just say that, yeah. We can say that. So let's just say that it's 2 joules. No. 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 No, it doesn't seem correct when it's 2 joules because it's too big. 2 joules is a very big number compared to the other guy. But it's 1 over kBT. Yeah, those guys would cancel. What is the KB actually? Yeah. Yeah, actually that's true. But that would be electron volts because like 2 electron volts is still something that you kind of should think about instead of 2 joules that you put inside your formula. That would be crazy. So I would say that it is electron volts. How does this compare to the vacancy formation in NGPT, which was given above as 0.96? So yeah, according to my knowledge, 0.96 is smaller than 2, which means that yeah, interstitial would be less common. Instead, the chance are no. It is not a chance. But yeah, you get the idea. It requires more energy. So yeah, that is basically from my knowledge. Okay. So, let's have the new artboard there. It might not be correct, it might be correct, but who knows. Okay. This one here. Um, let's go there. Place the There we go. Place it. There we go. So this one here is a pretty simple question. Could the jeweler be right? Based on the activation energy for interstitial formation and vacancy formation. In other words, could the atoms from the vacant sites have become interstitial defects? Explain your reasoning in one sentence. So, so yes. Um, according according to my knowledge, it could be true. In fact, like yeah, it could because like yeah, something. Wait. Um. So yeah, we were actually given that. How many sides are in the ring? So yeah. So yeah, basically that yeah. According to my knowledge, I- is that it could be true, although the chances are slim since it requires more energy. So that's just basically from my from my own reasoning. But yeah, you could say that you could just say that it's false because like yeah, it is rare. But yeah, I mean like yeah, I don't really just compare with others because like yeah, there is still a chance. So yeah, that's just basically from what I was actually thinking. So let's go into the next problem here. Number two, as we are now going to be talking a bit on glass. There we go. Let's enlarge this. There we go. Sketch the following on the axis provided. Okay. A cooling curve, molar versus temperature, for amorphous SiO2. And number two, a cooling curve for crystalline. Okay. So first things first, this one here is volume per mole. We 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 know about that, and yeah, and yeah, and yeah. For the x-axis, that would be the temperature. So so the so the cooling curve. Let's just go and just make this guy first. Oh, there we go. This guy and then this guy. Both of these here are amorphous because like yeah, that's just basically the graph. Because like yeah, this thing here is just actually just super cooled. And then right over here we could have like the transition there, and this guy here is the crystal. This guy here would be the crystalline. There we go. So yeah, I have labeled that. The first one, that's 1, the bottom the bottom side, that's 2, and then on your plot above, label the melting point. Okay, so let's just use a different color here. So this one here is the melting point, the MP. That is that is what I normally state. And then the second is the glass transition temperatures. So yeah, this one here, this could be like TG1. This one here, this would be TG2. There we go. Part C, list 2 ways you could change the transition temperature. Okay. First thing that you can do is the cooling rate. And then the second is the scission. I don't know how to spell it, but yeah. Putting oxygen in. Like yeah, putting some oxygen in could be actually become the scission. The scission, chemical scission, glass scission. I forgot what it is called, but yeah. But yeah, basically when you just put oxygen in, it would make it less viscous, I believe. So yeah, that is basically the solution according to my intuitive. So good. Next up, um, okay, we still have part D and E. So let me just go ahead and and just just add the new slide. Edit artboard. Add the new one. There we go. File place. The new artboard. Which is this question here. Let's just enlarge that. There we go. D. Tempered glass exhibits increased strength compared to regular glass. Consider a slice taken across a sheet of tempered glass. With reference to your plot, explain how the molar volume changes across the slice. Okay. So the molar volume would be actually different because at the far end it is cooled very fast, but then on the inside it is cooled pretty slowly. So yeah, it is not cooled at the same that. So explain how the so so yeah according to my knowledge it would be very dense, then and then after that it would be hollower, and then dense. So yeah, that's just basically how I would just explain how the molar volume actually changes across the slice. Because basically at the outside it is cooled very fast, which makes it not that dense because the volume per mole. So 1 mole. So yeah. I think so. So yeah, the first side there it is more dense, but then this one is less dense, more dense, and then less dense. That's according to my knowledge, okay? Because I don't really actually just mastered this, but yeah, I am learning. And yeah, this is how I will actually channel my mind. Which of the following stress strain curve could correspond to the tempered glass above? Circle the letters corresponding to your chosen curve. Okay, first things first. C. It couldn't be C. It couldn't be C. Because it has the plastic regime. No, sorry. It has the elastic regime. For B, it is elastic, and then just by sudden it just snaps. But then for A, it is always plastic until the yield point, and then it fractures. So according to my decision, it would be A. So yeah, that is my intuition, and that's how I just actually represent it. It might not be correct, but yes, for me, I don't care about how correct or incorrect it is. So yeah, that's that. Okay, problem 3. Edit artboard. Add the new artboard. Place the screenshot that I have. There we go. Enlarge it a bit. There we go. So, in Goodie Bag 8, we explored the impact of ocean acidification on pteropods by considering the dissolution of calcium carbonate in a citric acid solution. Now we'll consider a similar process, but using hydrofluoric acid instead. Hydrofluoric acid, HF, has a higher acid dissociation constant than citric acid. Write out the acid dissociate reaction for hydrofluoric acid. Label the conjugate acid slash base pairs. Okay, so let's just first write out that HF there, which is a solid here. This would dissociate into H plus, which is inside an aquifer, which means that it should be an H3O plus, but I don't care, plus the F minus, which is inside the aquifer. There we go. What is... Oh yeah. For the pairing, so yeah, I need to write the H2O. H2O, that's liquid. So yeah, this thing should be H3O plus. Let's just remove that out. There we go. H3O plus. There we go. Label the conjugate acid slash base pairs. Okay. So first things first, this thing here, it is an acid. This guy here, we know that's a base. This guy here is the base conjugate. And then for this guy here, that's an acid conjugate. Wait, what? No, that's the base conjugate. This is the acid conjugate. Yeah. And then for the pairing, that with that. There we go. And then this guy with this guy. There we go. What is the concentration of a solution containing 0.05 grams of HF and 0.1 liters of H2O? Okay. So yeah, we can just actually just realize that, yeah. The first thing that we are going to be doing first is to convert the grams into moles, because moles, it is the coolest thing. So yeah, we just need to actually change the thing. Let's see here. Let's go to the periodic table again. That is 18.9984, and then add that with oxygen, which is 1.00784. So yeah, you can just put it inside your calculator. 1.00784. Add them up with the fluorine, which is 18.994. Is that correct? No, 9984. So yeah, you will get something like around 20 for the MR. So the MR would be like 20.01 grams per mole. And so, how many moles are there? 0.05. Divide the thing by the answer that you got. So you'll get the amount of HF would be 0.0025 moles. And so the concentration would be 0.0025 divided by 0.1. Simple, right? Simple. So yeah, you'll take the answer, divide the thing by 0.1 liters. You'll get 0.25 big M. So yeah, there we go. And then C. If the dissociation constant for hydrofluoric acid is Ka equals to 7.2 times 10 to the power negative 4, what is the pH of the solution from part B? Well, yeah. We can actually just know what is Ka. So yeah, Ka of HF here is equal to the concentration of H plus and the concentration of that yeah, the other guy. that other guy, which is an F minus. Do we need to divide it by HF? I believe so. Divide it by HF. And then we know that actually the H plus and the F minus should be the same. So yeah, we could just say that it's x squared x, because why not? And then for the HF, it's gonna be 0.25 minus x. And so we just need to figure this out. 7.2 times 10 to the power of negative 4 would equal to x squared over 0.25 minus x. And then after that we just need to figure the entire thing out, which is something that I cannot do with my mind straight away. I should have actually gotten my calculator, but yeah, unfortunately my scientific calculator is nowhere to be found. So I'm gonna be solving this using a graph, because who hates graphs? 7.2 times 10 to the power of negative 4 must to equal to x squared divided by 0.25 minus x. There we go. We should get two values. There we go. Obviously it's not y equals 0. What? It doesn't cut when y equals 0. Wait, what? Well, yes. Just write like subtracted by y. That should work. Always. Yep, it works. What? So yeah, what you got is actually x equals to 0.01306. And I hope that's correct. So we know that the H plus is 0.01306, and so you just need to take the negative log of the answer. And the negative log the answer, which is 0.01306. That would be 1.88 what moles? Yeah, it seems so. Yeah, which would mean that the pH would be 1.884. So yeah, I guess that's the answer. So good. We found the pH. And so now we just need to go ahead and solve for the next one, which I need to go and just open up my new artboard and just place in this part E and F. There. Add in the new artboard. Boom. There we go. Place. There we go. Ha. Okay, so part E. If we had given you hydrofluoric acid, 7.2 times 10 to the power negative 4, rather than citric acid, 1.8 times 10 to the power negative 5, in the goodie bag, would you expect the shells to have dissolved faster or slower? Briefly explain why. Okay, so the shell is actually made out of calcium carbonate. And then the concentration is actually higher. Yeah, it is actually higher. Because like hydrofluoric acid is much more acidic than citric acid. Because like, yeah, it's just almost like 10 times. No, it is like 2 times. So yeah, I would say that faster because of much more acidic. And then part F. Explain what would happen to the pH of the hydrofluoric acid solution if it were to sit in a CO2 environment for a few hours, and why? Huh. Well, according to my logic here, the carbon dioxide will so the carbon dioxide would react to water, which would create carbonic acid. Yeah, because like, yeah, CO2 plus water would result to HCO3, which is acidic. And then you also have the other guy, the OH minus. No, wait. Carbon dioxide. Is carbon dioxide acidic? Yeah. Explain what would happen to the pH of hydrofluoric acid if it were to sit in a CO2 environment for a few hours, and why? Actually, I don't really know. Because like, yeah, the pH would be like some sort of a constant. What would happen to the pH? It would either precipitate, replaced by yeah. Actually, that's my yeah. So yeah, the pH would be, I would say, less acidic because of the carbon dioxide actually. reacting with the water to create a much more just to create much more acid, but then with that in turn would result into the common ion effect. Common ion effect, which would lead into the precipitation, which would mean that pH is less. There we go. That is according to my knowledge. It might be correct, it might be not, but yeah. But yeah, we are just testing a little bit of the logic skills. But yes, I don't know if I don't know if that is correct or not. But yeah, I am just sharing my thought process instead of the right or the wrong answer. Okay, next up, part 4. Problem 4. Wow. How many problems are there? 6, right? Oh, let's see. Oh, 5 problems. Good. That means that I don't need to spend like lots of time actually stressing about this. Okay. So this is about rate reactions. Let's place that. There we go. Place. Huh. There we go. So, to compensate for some of the oxygen consumed by burning the candle on one of your many Friday night dates, you decide to run a reaction that produces O2 gas as fast as possible. Okay. You recall 2 options. 2NO2 would result to 2NO plus O2, or O3 plus Cl would result to ClO and O2. You are able to find some information about the reaction of P. Its rate law is rate K and O2. Okay. So it's a first order. Use the experimental data in the table above about reaction Q to determine its rate law. Okay. So I am just gonna be using the quicker method. So yeah, rate would equal to K of a constant by the O3, the ozone. And then you want to try to find at what power that is, and it is in fact the power of 1, because like yeah, when you just see this here, this guy is multiplied by 2, but then yeah, this guy here would be multiplied by 2. There we go. That's simple. And then for the Cl, it is the same. This guy here actually multiplies by 2. That and then the rate also multiplies by 2. So yeah, the answer would be KO3 and then after that it's Cl. There we go. Okay, part 2. Overall order. The overall order would be 2. Because like yeah, it's 1 plus 1, logically. The value of K, the constant reaction. Ooh. This is something that I really hate, but yeah, we need to do that. So yeah. So yeah, we just need to find what K is. That's 10 divided by 0.07 multiplied by 0.25. So the K here would be 571.43, and then the units, which is 1 over ms. Yeah, 1 over ms. Over ms, so yeah, that's the units. Good. Well, that's quick. Good. And then we just need to plot this guy. Ah, okay. We just need to add in a new layer. No, a new artboard. There we go. File, place the new picture that I've gotten. There we go. B, plot the linear version of the integrated law that described 2NO2 result into 2NOO2. Label the axis, y-intercept and the slope. So for this, we know that basically this guy would be the ln of NO2. So yeah, that is just basically the principle, and then this guy here is time. I believe it's time. Let me just check that out. Yeah, it is time. So yeah, and then after that, this guy should actually go down like this. That should be the graph. The slope here should be negative k. And then the y-intercept here would be the natural log of NO2, which is where is it? Yeah, it is the initial natural log of 2. So yeah, that would wait, what? Enable the axis y-intercept and slope. So yeah, this is basically initial. Initial, there we go. And so yeah, the rest would be the same. So yeah, basically you just need to take the natural log of the initial, which you don't have any information with, but yeah, it's fine. And so yeah, that's that. If you have 2 moles of NO2, 1 mole of Cl, and 1 mole of O3 available, but you can only run one reaction, which reaction would you choose to produce oxygen the fastest? Justify your answer with one sentence. Ooh. Okay, if I can only run one reaction, I could just use the first, actually, wait, the fastest oxygen, that means that, yeah, you want to have the rate to be the highest. Let's just assume that no, we cannot actually assume that. You know what? You can actually assume the volume would be some random number, because like yeah, you, because like yeah, you can no. It is the change of rate. According to my knowledge, the fastest would be the second order, because it has like that and that. No. The volume would be the same. That's for sure. The volume would be the same. That means it's just basically just 1 times 1, which would be pointless. And so 2 would be better. So yeah, I would say it would be NO2. NO2. 2 is better than 1 times 1. That's my knowledge. Like yeah, I know it's so simple, but yeah, it is pretty fundamental, but yeah, it is just asking which reaction would you choose to produce oxygen the fastest. So yeah, my intuition would be to take the largest one, to take the largest order of reaction. So yeah, I don't know if the answer is correct or not, but yeah, who cares at this point. Okay, next problem here. This is a bit of XRD, which is the one that I'm actually waiting for, because like yeah, I haven't actually been doing XRD. So yeah, we can just go ahead and just do that. Place. And boom. Your research supervisor wants you to characterize two pure elemental powders she found in the back of the lab. Unfortunately, time on the XRD machine is very limited. To save time, you mix both powders together and perform XRD on the mixture. Oh, ouch. Okay. I guess that yeah, um that's that. From the plot, you have the following data to help identify the samples. You may find it helpful to add columns to assist your thinking. Okay. Use selection rules to determine the crystal structures of the samples. Assume sample 1 corresponds to the element with the lowest 2 theta peak. Okay, okay. This is something. Um, okay. Um, I don't know what to do first. The first thing that my intuition states is that you normalize the value and then you just remove the thing. So yeah, let's just actually just divide the entire thing by 0.049. So yeah, this guy here, the first one here, that would be 1. The second one there, 0.065 divided by 0.049, that's 1.3. 0.07, that's 1.43. Yeah, this guy here is actually 65. 1.33. Okay. And so, the bottom side there, 93. 1.9. And then after that, that's 131. That's 2.67. And then lastly, 187. 3.82. Okay. Oh wait. Um I do actually see two things. Let's just um yeah. What I see is that there's two things. Not really two things, but it's pretty clear, I should say. We can just first actually just multiply the thing by 3. So yeah, that is like around 4. 1.43. That is a weird number. 2. We could say that's 6. 2.67. Oh wait, that's a different one. Okay. Um That is around 8 over 3, so yeah, that's 8. 3.82. That is a random one. But then what I also realized was this one and this one here was similar. But but yes, unfortunately I don't know what it is. Assume sample 1 corresponds to the element with the two lowest theta peaks. So this and this should be the same. And then this guy here is something different. Actually 1.9? I don't think so. Zero 0.93. That's 18 point. Wait, what? Oh, 0.93. What you get is actually 1.8979. That's like around 1.9, to be fair. We can just assume that to be that. But yeah, let's just first actually just figure this one out. This one here, that one there, I recognize that as a 111. This one there, I recognize that as a 200. For the 6, it's a 211. I think that's a different one. According to my prediction, it is something different. And that one there is 220. Or is there any variant? No. Still no. Did I divide correctly? That is the first question, which I did correctly. Okay. To determine the crystal structure of the samples, 8 points. Okay. So, yeah. I guess one of them is actually an FCC structure. Yeah. One of them might be an FCC structure. But the other guy is something different. Let me just make a note of that, FCC. Because like with the lowest one would be a 111. In fact, yeah. The smallest one would be a 111 for the FCC. But when you're talking about BCC, the minimum would be 110, I believe. Yeah, 110 would be the minimum. But it could be something more. Well, yeah, from my recognition, this guy and this guy, it is 3 times. This guy and this guy here is 2 times. But I don't see any patterns regarding it. Except for multiplying by 10, which is something very useless. What just happened at 1.43 though? That is something pretty weird. I don't think that, yeah, two things occurs at a pretty near thing. I don't think so. Yeah. Let's see actually. Mm. Okay. One of them's 1, one of them's 2 times the thing. But what is the relationship with 1.43? It's 1.33. Oh. That might be something. Both of them is FCC. Yeah. From my assumption, both is FCC. Because when you actually just normalize using this value, that, like, yeah, this guy here would be 1.33, which would mean that that would be 4, and then this guy would be 8, which is basically the pattern that we just found. So yeah. From my knowledge, both would be FCC, which would be the answer. Okay, good. And then the final one. What are the lattice constants? Oh, wow. Let's add them up there. And just place the final one here. So I'll do that. And then I'll just close that up first. There we go. Hey, okay. Hello there, SDK. I didn't see you there. Okay. So yeah, let's just continue here. What are the lattice constants of the samples? Copper K alpha radiation. Wavelength equals to 1.54 angstroms. Was used. Show your thinking. Okay. The lattice constants. The lattice constant is the A. I know that fact. And A would equal to the square root of h squared plus k squared plus l squared. So, that. Actually, for the lattice constant, you can... Wait, you have the wavelength, which you can use. Oh, yeah. Sure, it's possible. Watch. So first things first, you got lambda. That would equal to 2d sine theta, according to the formula that was given. If you just follow the thing, and okay, there it is. That's theta. So yeah, it's 2d sine theta. So that means that you know what the d is. D would equal to the lambda. No, d would equal to lambda over 2 sine. Nope. It doesn't allow me to. It doesn't allow me to do that. So yeah, sine theta. There we go. Okay. We can just plug in the number. But wait, actually, we know what that is. That would be A equals to this guy. Multiply the thing by the square root of h squared. Yeah, that guy. By something, which in this case I would actually just take the 3. Yeah, actually, like, yeah, let's, yeah, taking, yeah, yeah, taking the square root of 3 should be the best choice, because like, yeah, that is the smallest one. And so with this, when we actually just plug the entire numbers in, I should I should get my answer. Yay. So let's do that. The lambda that we have here is 1.54 angstroms. Multiply that by the square root 3, which is the number that we select. Divide the thing by 2 of sine theta. The sine theta was given, so we should get that the first one is 0.049. But you need to take the square root of it. So yeah, square root of 0.049 and so that should be your lattice constant. There we go. So yeah, this one would be 6.025 angstroms, and then for this one here, that would be the square root of 0.70, which would be in here 5.04 angstroms, 1 for 1 angstroms. And that's it. Okay. So that's basically the entire thing. So yeah, that's basically the entire exam tree. So yeah, I know that there is some of the questions that I got wrong, but yeah, it's fine, because like, yeah, the goal of this is to actually just to train your mindset. So yeah, thank you, and yeah, so thank you very much for watching, and yeah, I will just see you guys on the next live work. Thank you. Goodbye.